Okay, in this video, we're going to focus a little bit more on graphs of trigonometric functions, but we're going to take a bit of a different approach. In the past examples, we've been looking at some functions that were written out, and we've been trying to visualize the graphs of those functions. We're going to do this the other way around now. I'm going to give us a picture of a graph, and we're going to try and analyze it to figure out what function it is, what transformations have been applied, and build the actual written out function from there. So we're going to do a lot of the same kind of things that we've been doing, but we're just going to do it in a little bit of reverse order. So let's start off with this example. There's a couple of things that we want to look for. We know we're going to be thinking about things like amplitude. We're going to be thinking about things like period. We're going to be thinking about things like phase shift. And we'll also need to think of what function family is this. Hopefully we can see that this is pretty clearly either going to be sine or a cosine function, depending on how we shift things. So this phase shift, we're actually going to likely end up with multiple different options. Let's talk through each of these things though. For the amplitude, we really just have to look at the distance from the middle of our function up to the outer edge, whether that's up or down. So we go up to the maximum or down to the minimum, and either way we can see that we're stretching this thing up by 4 units. So we're going to have this multiple of 4 on the outside of our function, stretching this thing vertically. For the period, our normal period is 2 pi. We're going to look at the period of this function, and we'll see if we can compare them to see, okay, what did we multiply? What I like to do here is to just highlight a portion of the graph, and we'll try and get the period from there. So maybe I'll start here at this intercept, and I'll follow my graph up and down. I'm not going to stop here because that's not enough of the picture to just start repeating the graph. I got to follow underneath and come back up, and that is enough of my picture. So really for the period, I'm looking at this horizontal distance from pi over 3 to negative pi over 3, and hopefully we can see pretty easily that that's 2 pi over 3. So our period is 2 pi over 3. If our normal period is 2 pi, then we can see pretty easily that we've just crunched this thing down by a factor of 1/3 or 3, depending on how you think of it. We don't have to look at that version of this. You could also go ahead and take a look at like maximum down to minimum, back up to maximum. And here you'd be looking at the difference between pi over 2 down to negative pi over 6. And you're, again, going to get 2 pi over 3 when you do this kind of thing. So that works out pretty nicely, counting that distance. And again, it doesn't really matter what portion you look at as long as you're looking at one full repetition of this function. For the phase shift, this is when we have to make our distinction about whether we're thinking about a sine or a cosine function. So the two parts that I've highlighted here are like the beginnings of the sine or the cosine function. So the part that's highlighted in yellow, you can see this was shifted to the left pi over 3. Or we can say the phase shift was negative pi over 3. And for the part that's this blue portion, you'll notice that it was only shifted to the left by pi over 6. Or we could say negative pi over 6 on here. So that shift will be important depending on whether we're looking at a sine function or a cosine function. From here, we can go ahead and set all of these things up. I'm going to have 2 options, so I'll write them both out. We're going to have our amplitude, 4, times the actual function. So let's do the sine one first. Sine of, now we need to scale our period. We're going to have this factor of 3 in here. And then we can think about our phase shift. Normally we have x minus our phase shift. Since our phase shift is negative, we have plus pi over 3. And then what you can do is just multiply this out. 4 sine of 3x plus pi. Or similarly, we could do the cosine version of this. And our amplitude stays the same. Our period factor stays the same. We're going to multiply by 3 on the inside because that's going to compress our period by a factor of 3. But our phase shift is going to be a little bit different. We have pi over 6, actually. And so what we have is 4 cosine of 3x plus 3 times pi over 6 is pi over 2. So either one of these is a fine version of this function. And there are other ones too. You can notice that we won't have to pick this version of the cosine function. We could start it here and we could say, well, actually it was a shift to the right by pi over 2, right? Or we could start similarly our sine function down here and we could say, well, actually this was a shift to the right by pi over 3. So all of these things you can mess around with. You can change the shifts whichever way that you'd like, but hopefully that works out to see. Now that you've done an example all together with me, I want you to try this one on your own. So we first need to think about what function we've got here. The nice part is that there really is only one option. This is the tangent function. We could say it's a cotangent function that got flipped upside down, but let's leave positive coefficients out front. So call this thing the tangent function. We'll find that scalar out front, a. I won't call it the amplitude because it's technically not an amplitude in this case. That's only for sine and cosine, but whatever. We'll need to find the period of this thing and compare it to what the normal period is of the non-transformed tangent function is. And then we'll have to look for a phase shift. So go ahead, pause the video, see if you can find what's going on, and maybe we'll remember this. Tan theta is really sine theta over cosine theta. That might be helpful for you while you're thinking about some of this stuff. All right, go ahead. Pause the video if you haven't actually done that. It's really important that you try these things on your own. Please. I'm begging you, pause the video. All right, I'm assuming you've done this thing now. Let's do it. I'm going to draw in these asymptotes. That's going to be super helpful for me because there's a couple of key points on the tangent function, and asymptotes are some of them. The other ones are these nice intercepts in here to think about. So let's think about the tangent function itself. I wrote this thing as sine theta over cosine theta. Why is that important? Because I know that normally when theta equals 0, that means that tangent theta is sine of 0 over cosine of 0. That's 0. So normally, my tangent function would start right at this point. But it's not now. It's shifted either to the left or to the right. Hopefully we can see that. Doesn't really matter which way that we go. Left or right phase shift by pi over 2. Now we can think about the period of this thing. Well, the period here, you're going to notice it's really just the distance that the horizontal distance that this portion of our graph makes. So it's really the distance between the asymptotes, right? And we can see what that distance is. Hopefully we can see that it's pi. So our period is pi. Now our normal period of the tangent function is pi. So that means we're not going to have any of those coefficients on the inside of our tangent function. For a, the amplitude, well, not the amplitude for this function, but you know what I mean, the scalar multiple, it's always a little bit tricky. I always look at this point right in here, halfway in between the intercept and the asymptote, and I'll look at the y value. This is normally, if we start at 0 and we have an asymptote at pi over 2, where cosine of theta is dividing by, or is 0, so our dividing by 0 on this tangent function, then normally halfway in between is at pi over 4, and normally sine of pi over 4 over cosine of pi over 4 is just straight up 1. So this is where we expect that point to be, and we can see it's not there. It's at a half. So that means we've scaled this thing vertically by a half. So here's our tangent function. It's y equals a half tangent. Notice there's no multiple here, so it's just x minus pi over 2. Or if you wanted, remember we could have shifted this the other way, and it could be x plus pi over 2. That's fine as well. Cool. Hopefully that example is something that you can see and follow through. We got one more to try. Hopefully it's not too bad to figure out what function type this could be. We've looked at sines and cosines. We looked at a tangent function. We talked about the cotangent function. So what one do you think this is? Probably secant or cosecant. And again, we're going to need to find that scaling coefficient out front, the period, and we'll compare it to our normal period, and the phase shift. All right, so again, pause the video, see if you can figure out some of this stuff. If you want, remember on our last example, it was really helpful to draw in some asymptotes, so maybe that's helpful here too. So I'll draw those in while you're pausing this. I know my lines aren't very straight. This one especially I got to fix. There we go. All right, if you haven't paused the video yet, go ahead and pause it. See what you can figure out. Okay, so again, we've got some options with our phase shift, right? Secant theta is 1 over cosine theta, and cosecant theta is 1 over sine theta. The reason I say this is that it's always nice to tell what your normal starting points are. And what I mean by starting point is what's going on when theta or x is equal to 0. On a secant function, we've got 1 over cosine 0, that's 1 over 1. So that means we expect our normal secant function to start like that. Our cosecant function, though, it's 1 over sine 0, so there's an asymptote. So you could either think about this point getting shifted to the right and scaled a little bit, right? But we'll say that would be where the minimum would be. So you could think about this point being shifted to the right by pi over 2, or you could think about an asymptote getting shifted to the left by pi over 2. And either one will work. So we can say left pi over 2. That's really a negative pi over 2 shift. Or we could say right pi over 2. And again, what we'll notice is that the one where we're shifting left is shifting the asymptote. That's where we would divide by 0. And the one shifting the right is shifting that point that would normally be at a y value of 1. Notice it's at a y value of 2. So that means our scaling coefficient out front is actually 2. Now we need to find the period. And a lot of people will take that advice that we had earlier and say, well, let's just look at the distance between the asymptotes. But the problem there is that this highlighted portion of our graph is not the whole thing. If we repeat this portion, we won't get the picture we have because we need the stuff above the axis as well. So it's actually the distance in between not a pair of asymptotes, but 3 asymptotes. We have to cross one here. Our normal period is 2 pi, and in this one, we have 3 pi over 2 minus negative 5 pi over 2. So what's that? 8 pi over 2, that's 4 pi. So you can see our period is 4 pi. We're multiplying it by 2, so that means we're going to need this scale coefficient of a half inside our function. So we've got 2 options. We can say this is 2 times the secant function. Now if this was a secant function, remember we were shifting this one to the right. So this is secant of half x minus pi over 2. And then we could say that's really 2 secant of half x minus pi over 4. Or we could look at the cosecant function and say we were shifting this one to the left by pi over 2. So it's going to be really similar. It's going to be 2 cosecant half x plus pi over 2. Or 2 cosecant half x plus pi over 4. Either of those will be good. Okay, so a quick summary on how to actually do this. There's a bunch of different things that we need to look at, but these 3 things are important. We need to find the repetition in that visual. I like to highlight things and draw in my pictures of my graphs so we can really see what's going on with there. Try and find the horizontal length that it takes for that function to start repeating, and be careful. Try and just draw the repeats and make sure you actually get what your function is supposed to look like. Then we have the amplitude, or the scaling factor, for the non-sine and cosine functions. And really what you're doing here is you're looking at some key points and comparing y values. With the sine and the cosine, that's really the maximums and the minimums. They're normally at 1 and negative 1. Where are they now? With the tangent function and cotangent function, I like to look at those angles pi over 4 or negative pi over 4 or whatever, the halfway point in between the x-intercept and the asymptote. And normally, those will be at 1 or negative 1 for the y values. For the phase shifts, we do the same thing. We're just going to be looking at the x values here. So compare where x-intercepts are supposed to be normally with where they are now. Compare where asymptotes are supposed to be normally with where they are now. Those types of things. Then just make sure you keep your algebra straight. Make sure that you actually do the distributive property on the inside, right? We keep our multiple on the period here factored out of our phase shift, and then we can multiply it all through so it doesn't look perfect at the end. But keep in mind that kind of stuff. Hopefully this is helpful to just get a couple of examples of running through this, looking at pictures of graphs and grabbing the function from there. This is a really important skill that we'll need to just visually identify what's going on. So again, hopefully that's helpful before we move on.